So the important point is that if you want to know or maybe observe whether or not the approach that you are interested in is an unsupervised learning problem, observe two things. First, there's no ground truth associated, no measurements whatsoever. And second, it's very subjective area. Like clustering is quite subjective. For example, if I ask 40 students to maybe group together, but there's no overlapping between them. Of course, the maximum number of groups is 40, but they can arrange whatever they like. They could group together as one group. They could divide into two or whatever, depending on their preference. That is why clustering is one of the problems that is cast as unsupervised learning. There's no actual target that could best specify. It's like it depends on the situation. Dimensionality reduction is also another thing that doesn't really have like a target. Let's say, for example, if you want to reduce the dimension of your input feature, you can use tools such as PCA. Have you learned that before? If you use PCA, you probably remember that you can somewhat project your maybe input vector on some basis. It would reduce or maybe it would project that information into important dimension. That was the principal axis. And with that axis, there's actually no right or wrong. It's just like you can project as much as you can or you cannot project at all. That's all it is. So the only rules that you have is like the orthogonality. That is the rules. Or maybe data correlation, that's the rules. But there's no other thing else. There's no target variable that you can use to guide you how to supervise them. And yeah, just like what I said before about data association, the recommendation system, that's what data association is like. What is the similarity point, picture to this cup? What is the similar things to this remote? It's all pure preference. Or maybe it depends on how big your data is. And usually to find data association, we will use correlation between maybe representation vector. For example, if you take a picture of this maybe remote, and you're trying to find the other object that is a remote, you can actually find the correlation between pictures. And you try to find where is the most correlated object in an image, then you'll find it. But that correlation has no target value or label. It just most correlate to the least correlate. That's why it's unsupervised learning. Right, so that's it. But today we'll actually go over these two, and PCA probably be something that we will learn in next week. Actually, PCA is, how should I say, it's like a general way or maybe a general approach to perform dimensionality reduction. But there are so many other ways that you could do, but maybe PCA provide like a foundation as to how would you project your information such that your reduced feature dimension would well represent your original data. That's what PCA is for. And actually, if you think about the other two application of dimensionality reduction, when we talk about visualization, just think about that you have maybe n-dimensional feature and you want to visualize it in 2D, maybe 1D, one-dimensional visualization, or you could do two-dimensional visualization or three-dimensional visualization, but probably not more than that, because that's the best human can interpret. Like the hardest possible is probably 3D. 2D is probably good enough for us to understand what's going on, and actually 2D is probably the best when you want to present it on paper. But 1D would be too simplified. It's like it's overly simplified. You may not get all the aspects about the feature that you're looking at. But if we talk about data compression, it's probably being that you have n-dimensional feature, you want to reduce it to maybe p-dimensional features, but it's usually being p that is much less than n. So that's usually being the condition. So yeah, that's like a little bit of what we mean when we say we want to deal with data visualization or then, data compression. Just that. And yes, today we'll go over these two techniques about clustering. First of all, I think we should talk about what is clustering task by definition. So by definition, let's say if you have many data samples, you can say you have, you have xj. I'm not sure why they have this. I'm not sure what's going on with my slide. Okay, you have xj, j from 1 equal to m, and each xj is a two-dimensional array, such as, maybe I swap the direction. Okay. Maybe I'll put it this way. Like for a J sample, you only have two-dimensional representation for the feature. Right. Therefore, you can actually provide scatter plots for all of your training data. And by the way, all the clustering algorithm here, most of them we are talking about the training phase. When we do inference, we will not see the actual clustering of your data, but it's more like how would you categorize that particular samples. Okay, but first of all, let's look at this and know that it is actually data samples in training. Okay, so we know that it's in two dimensions. So that means this is x1, this is x2, right? And we can probably provide scatter plot like this. So what is clustering algorithm does is actually, receive these data points and provide the cluster. Actually, this output is one possible outcome of your clustering. If your clustering algorithm cannot find clusters at all, let's say if m is 1,000, you probably end up with having like the output that is containing 1,000 clusters. But if your clustering algorithm can somewhat cluster your data into groups, let's say in this example, they can provide you 6 groups. So yes, you can, color them to denote that, okay, this is the clustering of the data. Or maybe, for example, if you feel like, well, this clustering algorithm kind of, overly clustered. Cluster, how should I say, it's exaggerating the groups. For example, maybe these two should be grouped together. So maybe this clustering algorithm is not suitable. Maybe you have to change parameters so that they are together. Or maybe you may say that, oh, actually, yeah, it's kind of work, but some of these data samples, perhaps these clusters, we should not call it cluster because it's outliers. Something like that. It depends on what you know in your data. And usually clustering algorithm will be like a very first tool that you use when you want to annotate your training data samples for supervised learning. For example, if you collect images of cats and dogs and maybe you want to provide the breeds, of course you can collect them, you can extract the feature just like what I showed here, and then we can do some kind of like clustering. And what would happen is that, okay, you probably end up with so many points that are grouped together, right? But the thing is, what I was going to say. The thing is, yes, you may be able to group, your output, your outcome, but thing is, the way that it's clustered here, I mean, it depends on your goal. Do you want to consider birds as part of your group, or you don't want to? If you don't want to, then it becomes outliers. If you want to, then yes, it's part of your output. And usually it's like you can use this clustering to provide like an overview of what your data look like. As I mentioned before, if you take pictures of cats and dogs and you want to, provide some labeling, you can use these tools to first categorize your data samples. I mean, if you didn't keep it well, there may be some mixture. So this clustering algorithm can help you separate your data samples at the beginning. And after that, you can start provide more labeling or maybe perform some post-processing to make it more accurate. And actually, what I wrote here is like, okay, in this example, very first one that I introduced to you, is like the example where you have your data points that has input features that's only in 2 dimensions. So it's easy to see how clustering is actually going on. But if you are dealing with images that actually have 3 dimensions, I mean, the most directed way is probably to use maybe color, but well, RGB may work, but it's like you have to use every pixels in an image. So that means that your features dimension is like 3 times, maybe if the size is 64 and that size is 64 pixels, then your input feature will be like 3 times 64 times 64. That is your input feature for one sample, which is very high. Like you can't really visualize them. So one way to do it is to actually maybe extract the important features out of the image. That's maybe your first step. You can use various ways, like you can use machine learning or maybe deep learning to extract some features first, and then you maybe use those features as the representation of that image. But in order to visualize, and here I say only for visualization, you may have to do something called dimensionality reduction to compute from this high dimension and project it to 2D. However, your clustering algorithm can start working since that after you have extract your feature. Okay, or you can use this high dimensional image as your input feature to the clustering algorithm. You can do that as well. You can do it many ways. Like you can use this feature directly as your input, or you can feed this input into some neural network to extract the feature. You can use this as input feature for clustering. Or actually, but this is more like for visualization, you may be using this input or that input, but you find a projection matrices and you use that projection to reduce dimension to 2D for visualization, or maybe you can use this 2D dimension to then do the clustering. So there are many, many ways to play around this, but usually if you have something of high dimension, people will suggest that you do something like feature embedding first. Feature embedding is like when you extract your features. For example, but I wonder if you ever have experience with feature extraction before. Actually, if you so not yet, right? Okay. You used deep learning before? No. How should I say? How about coefficient of Fourier transform? Discrete Fourier transform? Not yet.
Fourier transform.
Fourier transform. And wavelet? Not yet. Okay, but that's okay. Maybe, okay. If you remember our deep learning that we've done on classification task, before the deep learning would provide you the class, or maybe to do the regression before that final layer, if you maybe bypass the output before the final layer, then it becomes some kind of feature. But it's like the feature from your neural network. You can use those features as a representation of your input as well. But anyway, don't worry. Because today we will only focus on performing clustering. But what I'm trying to say is that, yeah, usually people would do some kind of feature embedding or feature extraction before we actually use that samples to perform clustering. Okay, so yeah, right now we kind of know what clustering is. Okay, first of all, let's start with k-mean clustering algorithm. So what k-mean clustering algorithm is? K-mean clustering algorithm is actually a clustering algorithm that clusters the data samples based on the centroid. And the centroid of your clustering algorithm, which is like the learned parameters from this algorithm, will be the thing that you use when you perform some kind of inference with the clustering algorithm. Okay, let's assume that you have performed some k-mean clustering algorithm on your training samples. What you get from this algorithm will be the centroid of the cluster in your training samples. For example, if I correctly assume that there are 3 clusters, then you get 3 centroid like this. And when you do the inference, you probably throw a sample point in, like let's say here. And what you do is that you measure the distance between your input centroid with the rest of your centroids of the other cluster and see which cluster will have the centroid that's the closest to your input samples. So let's say this yellow point is the closest to this red point. Therefore, this red point should be clustered as the yellow cluster. Not green or not pink. So yes, the output from your clustering learning, and I'm not sure, it's like the output of the learning phase or the training phase is actually the centroid of each cluster that could happen, or maybe that already happened in your training data. Another parameters, which is more like a hyperparameters, is how many clusters are there. For k-mean algorithm, it is one of the algorithms that you have to specify how many clusters do you think there are. For example, in this example, there are 3 clusters. That's actually given by the user. You can also specify 2 clusters, and probably you will get these 2 clusters as one. And yes, again, you do the same. Like, for example, you maybe evaluate this point against this cluster and that point against that. Maybe you have a new centroid here and see which one is the closest to your input. Yeah. So yes, the performance of k-mean clustering depends a lot on how many clusters that you pre-specify. In order to find the correct k, you have to find it on validation set. So you run the testing on validation multiple times to see which number of clusters is the best suitable for your data. So it's purely data driven in a sense. Okay, let's go over how you actually train the k-mean clustering model. And please don't forget that the output of this training is the centroid of the clusters associated with your data. So in the first step, let's say you have the data samples that look like this black dot. Right, so that means you don't know if there are clusters at all, but you kind of presume that there are 3 clusters, that is this pre-specified parameter. After that, you will randomly initialize each point to a cluster among the 3 clusters. After that, you compute the centroids of all those points that belong to each cluster. So in this case, there are 3 clusters, therefore there are 3 centroids compute. And after that, once you have this centroid, the algorithm will then recompute the centroid again using the data that's supposedly being in that cluster. And do it again until that centroid kind of move to the center of your clusters. And then when the centroid does not keep changing, that means that you have the algorithm that will work for your data. And the reason that I said that, when the centroid stop changing, that means that you should stop training. That is because that means that this centroid is probably best representing the clusters of your data. Shall we continue?
Yeah.
Okay. Actually, the algorithm is written here. So the initialization phase will be something that, kind of like you do it one time. But in this starting phase, you will probably iterate between step 1 and step 2 until your centroid is stable. So for example, you start off with assigning the number of clusters, then randomly initialize each point to one of the clusters. After that, you will iterate the following. Firstly, you compute the centroid. After that, you will assign the training samples that's closest to that particular cluster to be in the same, so to that particular samples to be, okay. You assign the training samples that is closest to that centroid to be the same cluster. And after that, you will go back, compute the centroid again, and check which training samples should be included in that cluster based on the fact that it is the closest to that centroid. So the process would go like that. So that's how it works. Thing is, and what does this all mean? Actually, this algorithm is made for solving this optimization problem. And thing is, this is the main objective problem that you would you would formulate it if you want to do clustering algorithm, because it will try to allocate your data samples to a particular cluster, or C subscript say K here, such that it's closest to maybe a representative vector, or in this case, it's your centroid. So that is like the mathematical formulation. But as we know, and I believe that you remember from last time, optimization problems like this, where you actually, have the variable to be something like regions or maybe set of points, is actually a discrete problem. So you can't really solve it directly. You have to use some kind of algorithm, and the k-mean algorithm are one of those algorithms that can solve this problem. The other equation that I wrote here is more like when you extract it onto each feature dimension, but I think going over here is a little wasting time. So I kind of prefer looking at this one because everything is like in one sample. Yeah. Yes, so I think that's all. Let's have a break before a break. Just a little bit. As a side note, please don't forget that for this k-mean clustering, k, or the number of clusters, is going to be one of the hyperparameters, and it's actually very important. Another thing that we didn't mention is the distance function. Right now, generally we use Euclidean function as the Euclidean distance, but you can use other distances functions as well, or how you define the centroid of each cluster is actually another hyperparameters, but this one is just like the average location of the samples within the clusters. So that is it for the k-mean clustering. Okay, let's have a break for like